Okay, one more definition before we compute some greatest common divisors. So when you compute a GCD, you with the Euclidean algorithm, you get some polynomial. Usually what we're going to do is we're going to require that instead of using the polynomial it gives us, we take that polynomial and we divide by the leading coefficient. That is, we want to make our polynomial or our greatest common divisor monic. So let me define for you the greatest common divisor in the context of polynomials. It agrees with all of our other definitions, but just to be clear, we can use the word the, that is, there's one and only one, if we enforce this monic condition that I'll explain here in a second. All right, so suppose that, f is a field. We need to be able to divide, so we need a field. And we have two polynomials here, not both 0. Then the, emphasis on the, greatest common divisor of f and g is the monic associate of a greatest common divisor. And monic here just means that the leading coefficient is 1. All right, so I think this is best understood with an example, like all things. So let's do an example. So let's take the polynomials x to the 4th minus 1 and x to the 4th plus x, and let's view them as polynomials here. Then what's going to happen? Well, if we do one iteration of the division algorithm, we'll find x to the 4th minus 1 is x to the 4th plus x plus negative x minus 1. And we will find that when so here's like our first remainder, here's like our r0, and here's like our r negative 1, and here's like our r negative 2. If we divide r0 into r negative 1 now, we're going to find we get negative x cubed plus x squared minus x times negative x minus 1 plus 0. We got 0. So the GCD is the previous step. So our greatest common divisor is here. This is the GCD. And I guess I said the, but it's not the, it's a GCD. So the Euclidean algorithm tells us, or the polynomial Euclidean algorithm tells us, that negative x minus 1 is a GCD. It is not the GCD, though. The GCD would require the leading coefficient be a 1. So we can remember, if we multiply through by a unit, it's still a GCD. So what we're going to do is we're going to say the GCD of x to the 4th minus 1, oops, I should put a comma here, x to the 4th plus x is, well, how do we make the leading coefficient a 1? We multiply through by a negative 1. So that's x plus 1. So this is the monic, it's actually unique, the unique monic associate of what the Euclidean algorithm spits out. It's monic, of course, because the leading coefficient is 1. You can always do this. You can always take your GCD and divide by the leading coefficient. In this case, it was the same as multiplying, but in general, dividing by the leading coefficient to force it to be 1. And so we will refer to the unique monic associate as the GCD. Okay, so the with an emphasis on the one and only one is that one. So here's an example of computing a greatest common divisor with the rationals. There is a more in-depth example in the book, so I won't, these get pretty complicated fast. Let's do an example where the arithmetic is easy, though. So there's another more in-depth example using Q in the book. We're going to do one over a finite field. So let's look at the polynomials x to the fifth plus x to the fourth plus 1 and x cubed plus x viewed as polynomials in the finite field of order 2, or over the finite field of order 2. All right, so the rule is we carry out this repeated division. Okay, so we divide x cubed plus x into x to the fifth plus x to the fourth plus 1. We've done this already once, and we got this expression. So here is our r0, our first remainder. Here's our r negative 1, and here's our r negative 2. And now we divide r0 into r negative 1. And when we do that, what we're going to get is x plus 1 times r0 plus x plus 1 is r negative 1. So here's our r1, here's our r0, and here's our r negative 1. We still haven't gotten 0 yet, so now we're going to divide r1 into r0. Oops, I don't know how that came about. X squared plus x plus 1. So that's our r0, and we're going to divide x plus 1 into it. And what we get here is actually x times x plus 1, and then plus 1. Again, let me label this. This is our r0, r1, and this is our r2. And now 1 is certainly going to go into x plus 1. So whenever you get a constant, you're basically done. You know the GCD is 1. But nevertheless, we'll write it out. So here's r3, here's r2, and here's r1. Great, so this tells us then that the GCD, since we got 0, is the remainder from the previous step. And this is already monic. The GCD is 1. In particular, these polynomials, if you remember the terminology, the same terminology applies here. We say they're relatively prime. They have nothing in common. So that's an example working over F2. And then lastly, let's do an example working over F3. And we're going to do the same polynomials, just viewed as polynomials with coefficients in F3. And let me just remind you the arithmetic here. So 1 is the same as, or negative 1 is the same as 2, negative 2 is the same as 1, and of course 3 is 0 here. All right, so again, we do the same thing. We first start off by dividing them. And when we divide x cubed plus x into this, we're going to get x squared plus x plus 2 times x cubed plus x plus 2x squared plus x plus 1. So that's what we'll get when we do that division. Let me label remainders here. That's r negative 2, r negative 1, r0. Now we're going to divide r0 into r negative 1. And when we do that, we're going to get 2x plus 2 and 2x squared plus x plus 1, and then plus 1. And we can actually stop here. Oops, not that. So this is our r0, and this is our r1. We can stop here because this is a constant. Whenever you get a constant, you know that the next step is going to terminate. So from this, we learn that the GCD is still 1. Although this Euclidean algorithm actually finished faster than the previous one. Okay, and you can go in and check my arithmetic to make sure these factorizations are right. But for example, just to make it clear that we're working over F3, if we look at the leading term here, 2x times 2x squared is 4x cubed, but 4 is the same as 1 in F3. Okay, so you can go in and check this arithmetic, but it will work out for you.